It is my pleasure to introduce tonight's speaker. Tonight, we are pleased to be joined by Dr. Marley Dewey, Associate Professor of Bioengineering at UC Santa Barbara. Marley earned her Bachelor's of Science in Chemical Engineering from the University of Maine and her PhD in Materials Science and Engineering from the University of Illinois, Urbana-Champaign, where she was a National Science Foundation Graduate Research Fellow and recipient of the Annual Innovation Award for Outstanding PhD Thesis. She later served as an NIH Clinical and Translational Science Fellow at the McGowan Institute for Regenerative Medicine at the University of Pittsburgh. Her research focuses on developing biomaterials and nanoparticles to improve human bone repair, treat disease, and restore coral reef ecosystems. Please join me in welcoming Dr. Marley Dewey.
Thank you so much for the kind introduction. So I like to start my talk with a bit of a more personal story and how I got interested in this, repair of coral reefs, since a lot of my background is more in personal medicine for, human repair. Growing up, I did a lot of swimming, so my family is all a bunch of swimmers. I still am a competitive swimmer, so you would imagine our family vacations probably looked a lot like this, so going out and doing swimming, and that's exactly what we did. So I remember when I was younger, I was fortunate enough to see a lot of these beautiful coral reefs, and I remember being inspired by their beauty, the number of different creatures in the ocean, and it was overall just like really, truly a magical, experience. And then flash forward many years later, I'm in graduate school, I'm doing research in biomaterials for more bone repair, and I have a conference that's in Hawaii, and of course I'm super excited to get back to the reefs, escape the conference a little bit, as I probably shouldn't have, but I still did. And overall was excited to see these again. But unfortunately, what I did see was this. So this is a picture that I actually took myself when I was a graduate student. So this is, you can see back in 2021, so not that long ago. And this is in Hawaii. And what was truly devastating was it went from this beautiful, lush, kind of almost underwater forest to then this like desolate sort of, there's not a lot of colors, there's still some fish, but it almost looked like a bomb went off underwater, so there was a lot of debris around. And so this was truly devastating, and even just months ago, I actually was in, or just a month ago, was in Puerto Rico, and this is where I initially was inspired by these reefs, and this is what I saw. So back when I was a graduate student at the time, I felt very, motivated to do something about this, but I was in this field of, regenerative medicine for human health. And so I didn't really see this connection, and it was something that, always bothered me. So a lot of the work that I did looked like this. So it was building these materials to repair our bones. And I remember it was when I was working on these, I started to think, these kind of opaque materials look a little bit, if I stretch my mind a little bit, like these bleached corals might look. And they have like this nice porous architecture that I could kind of see in these corals as well. But I remember bringing this up to my advisor, and I was like, hey, has anyone ever used biomaterials to, repair coral reefs? And he was like, what are you talking about? He's like, we're not doing that. That sounds insane. And I was like, okay. And so, I kept that in the back of my mind, and I was like, this is something that I would love to do later. And I, of course, wasn't going to quit my PhD either, because my parents reminded me that I wouldn't make any money as a marine biologist. So I waited. And I waited until I could make my own lab and I could do whatever I wanted to do, which was, combining these things to repair coral reefs. And so this is what my lab looks at right now. And at the end, I'll talk about a variety of the other projects that we do. But one of the ones that I'm really going to highlight today is this repair of coral reefs. And so when I started to think about how this could actually become a reality, so how I could take my knowledge of bone repair and then transfer this to coral reefs, was after some literature searching. So one of the first things I found was not people making biomaterials for coral repair, but actually the reverse. So people have taken coral and they've ground this up and they've put it into people's bodies, and you can get better bone repair, which is really interesting. And some people have even said that it could be an ideal bone graft substitute. You can always talk to me later about that, whether or not I think that's true. But there is still enough people out there doing this. There's companies that even just grow corals to put into people's bodies, that there is something there. And how this is possible is through a few different reasons why these are actually so similar that you can get bone repair. So if we just look at our coral skeletons and our mammalian skeletons, sure, yeah, they look, white if they're both bleached out. This picture, they kind of look similar. But if you actually look closer into the porous architecture of these, so this is a scanning electron microscopy image, so getting really close, you can see that scale bar is on the order of microns. We can see that these look almost indistinguishable from each other. So there's this really similar architecture between our bones and corals. And so this big premise to a lot of my ideas was, okay, if we've used coral to heal human bones, then why can't we do the opposite? And so that's not using human bones to repair corals, but it is taking what I've learned about bioengineering and biomaterials and transferring that to repairing corals. And why I'm interested in corals and not just, for coral repair and not continuing down this route of bone repair is because our reefs are, an essential ecosystem that is facing this rapid decline. So they provide, a ton of resources for people. So they serve as a buffer for storms, so protecting people that live on the coast. They also provide us with, food from fisheries, and they're also, a draw for tourism, which was, me as a child and still is. And we can see that over time, we've had this dramatic decrease, and in general, they provide just so much money for both worldwide and the U.S. economy that it makes sense that we want to combat this decline. And to really get across my point is back in 2014, and then just a few months later, some other researchers took some pictures of coral reefs before and after a mass bleaching event, and this was due to a heat wave. So you can see just over the course of 3 months how, even though these reefs aren't as vibrant, that brown color is actually still a good sign of health. But then we see that all of this is gone and we're left with just this skeletal field behind. And so we obviously don't want this. And the problem being that our current repopulation methods, so like how to regrow all of our reefs, are pretty ineffective. So people will use these inert ceramic plugs, so basically just, a ceramic tile. They'll chop off a piece of coral, they'll place it on this tile, and then they'll just let it grow over time. Other people will also hang these from trellises. So again, like the nice part about coral being kind of like you can snap off little pieces and it'll just grow from that piece. And then people will take these pieces and then transplant them back into the ocean. And they might secure them even with zip ties, but one of the issues is that the actual survival of these when you bring them back into those other locations in the ocean is pretty dismal. So I think only like 60% of these might survive that process. But there are slow-growing corals that have improved survival against all odds, so against our changing ecosystem. They can still have this better survival than some of these fast-growing ones. But the problem is the reason we can't use these is because they grow just so dramatically slow that it would take way too long to repopulate our oceans with these. And so the premise of a lot of my lab's research is, can we take this inert material that's not really adding any substance or any sort of direction towards like accelerated growth or repair, and can we build this new material that essentially will help our corals grow much faster? And so how we do that is by taking inspiration from biomaterials and bioengineering. And so for those of you that aren't as familiar with biomaterials, I'll talk a little bit about biomaterials in the medical landscape and then transition this to corals. So biomaterials are essentially a material that's designed to interact with tissues in your body. And so these can be as a way to treat, an injury or repair a tissue, or even sometimes replace a whole tissue. They can also be used as a diagnostic, but most of what I'll talk about is more of the reparative elements. And so many of you might actually even have some of these biomaterials in your body or be using them right now. One of these is hip replacements. So hip replacements are considered a biomaterial. You've got this metal that you've now added to replace your bone. There's also some tooth replacements that can be considered biomaterials. Vascular stents, to help with these clogged arteries. Contact lenses are a great example of a biomaterial as well. And then skin grafts. So these might not be as common, but these can be some very biologically based materials to help you regrow your skin. So some of these are acting as inert sort of materials, and others are actually working with your body to regrow tissues similar to the skin graft. So if we look at this timeline of how people have developed biomaterials, say, for bone repair, this has actually taken decades. So it started off with metals, then people examined ceramics and some polymers, and then started blending these together. And then finally, a lot of new research has been in this tissue engineering field, which is what my lab focuses on. And so this is how I see we could use this kind of jump start towards coral. So instead of, this where we're at with these ceramics, we could jump start our repair of these by focusing more on tissue engineering principles. And so there's a variety of different biomaterials that exist, and that determines, how you might be repairing a tissue. So if we're just thinking about bone, there's some of you might have even experienced one of these before. So autografts is when you take bone from somewhere else in your body. And this could be any material too. It doesn't just have to be bone. And of course has this great biocompatibility, but obviously if you have a missing portion of bone and then you're taking this from somewhere else, you now have 2 injuries in 2 places that you have to repair bone, and that's not ideal. You also don't have a ton of bone to just for spare. And then there's allograft, so this would be from a deceased donor. It's similar to your native bone, but of course I can't just take my friend's bone and put that into my body and expect good things to happen. You have to process this a lot so that your body doesn't respond in a terrible way. But that removes a lot of the great things. And so that's where biomaterials come in, where you could look at ceramics, which, all of these have their strengths and drawbacks, but, these ceramics being pretty strong, our metals being even stronger sometimes, and then polymers giving you this nice tunability, but sometimes causing some, adverse responses. But a lot of what my lab does is focuses on polymers because of how tunable these are. And so what are polymers? They can come from nature. So collagen is all throughout your body. That's a polymer. You can get the chitosan from crustaceans. There's cellulose from plants. And then there's algae or alginate from this brown algae. And then there's also synthetic polymers. Some of these you might have seen before. So sometimes people will 3D print with these. There's also some that have been used even in laxatives and whatnot. But these are all very, very tunable. And what's exciting about these is because you can tune them so well, you can actually get them to be bioactive and to mimic the body. So as an example, if we're thinking, say, about contact lenses. So the first iterations of these were basically this blown glass shell that was floating in a sugar solution. And someone said that it was large and unwieldy, which, I've never worn a contact lens, but I can't imagine putting a glass ball in my eye. That sounds terrible. And then in the future, people made these into hard plastics, and they were pretty rigid, but that was still an advance. But if we think about what are the actual properties of the eye, so it's this soft tissue, it has to rotate around, it has this very moist environment, and you also have to have this transport of gases. If we are then trying to make a better contact lens, we would want to take these properties and design a material that then is addressing them. So one could be the fact that we now have these soft, flexible, and smooth contact lenses, because that's addressing the fact that your eye is soft and it is not as hard as glass. Another is, a high water contact. So some of these contact lenses are like, floating in this solution, and so they're moist because your eye is moist. You don't want to be putting something really dry in your eye. That just sounds terrible. And then they also are gas permeable. So all of these are essentially, when you're thinking about, I want to make a material to help repair a tissue, you need to be thinking about, what are the natural components of that tissue that you can then capitalize on to make the best material. And so some of these features that you want to look at include the material type, like I just mentioned. How porous is this? So does it have a lot of holes in it? And then is this something soft or stiff? Like, what are the general mechanical properties? And so this is an example of how some of these properties even tie together. So you can see if you have something that's, not very porous, it can be very rigid, but then something very porous can be very flexible. So some of these kind of go hand in hand together, but it's important to know what are the natural properties of what you're trying to repair. And that's hence why a lot of our medical devices are how they are. Another aspect of this is even just how the structure of your tissue looks. So this is like from a company that tries to make various different structured materials. So you can see these are 3D printed. There's one that has a lot of, crisscross, and then others that are in this like nice aligned structure. You can actually put your cells onto these, and you can see how your cells respond to this. You can see with this crisscross material, your cells are kind of everywhere. But with these elongated sort of materials, your cells also elongate. And this is important because the different materials or the different tissues in your body also have properties like this. So like your tendons are very aligned, whereas your cartilage is more of like this meshwork. This is also important for the immune response. So this was a study where they looked at different sort of roughnesses of just a metal implant, and these are immune cells. So this would be, some of the immune cells in your body just placed onto these materials, and you can see how on different surfaces your cells even change shape. And this shape change can change then how they behave in the body. And this might mean that you get rejection of what you put into your body, or it might mean that your body senses this as something that it really likes. So how even just the surface and these pores on your material matter a lot. And of course, this is biology, so biological elements matter a lot as well. And so at least for bone, there's things like mineral plays a huge role, if you're using collagen or not, which is one of the major organic parts of bone. And then if you're using some of these growth factors or these proteins that cells use to repair, so this is an example of one, bone morphogenic protein 2, which your cells will use to actually help guide them towards making bone repair. So if I'm thinking about, using bone as an example, because it is very similar to coral, how I would go about, repairing this, I first want to look, what are the properties of bone? So we can see this cross-section of bone. There's this very stiff, very not porous region on the outside, and then on the inside, there's this cancellous part, which is very porous and also less stiff because it is so porous. And so in your long bones, this is where you'll find a lot of your bone marrow, but even other bones in your body will have this sort of structure as well. And then bone has mineral, it's like calcium or hydroxyapatite often, and then glycosaminoglycans, which are essentially sugars, and then, like I mentioned before, type 1 collagen being the main sort of organic makeup of your bone. And so as an example of how important just mimicking this can be, this was a study that my graduate lab completed where they essentially wanted to make a biomaterial that could better repair large-scale bone defects. And so we made a scaffold that had just collagen, and then one that had this calcium and phosphorus mineral, as well as collagen. And so it's basically a mineralized collagen scaffold and a non-mineralized collagen scaffold. when they put these in these large-scale defects in rabbits, you can see here that the scaffold only, these are micro CT images, there's still this like big gap in that skull region. And so that's because the bone has not fully gone back into that scaffold and made new bone. But we can see with our mineralized collagen that we actually have more of this new bone occurring, so there's more filling in of that empty space. And this, of course, wouldn't be an engineering presentation if I didn't have a graph, so don't worry, there are more. And so we can see here just how significant that difference is. So if you can't just, take my word for it with the images, actually analyzing this, we see how much more significant bone we can get. And this is because, like I mentioned, bone is comprised of mineral, and then these mineralized collagen materials are mimicking the mineral properties of bone, and so we get more bone repair. And this is important because if I'm thinking about trying to make a material for coral reef repair, I need to be thinking about these similar concepts. And to kind of end with some of these more medically focused paradigms, so the tissue engineering paradigm is really interesting, where you can essentially isolate patient cells, you can expand these, you can put them into a material, you can add some potentially other active, bioactive signals, and then you can add these back to the patient. So it's like their own cells in a material helping with repair, and then you put that back into the wound space. And so there are companies that do this, maybe not all of the aspects of it, because still a lot of this is in progress, but there are a lot of companies that have these bioactive materials that are working with your body with these tissue engineering principles. So one is like Integra has a lot of wound matrices where they'll essentially, this will work with your body to repair, a skin wound. There's some that are based on placentas even, so you can take placentas and you can use this again as a way to repair your, if you have injuries. And like I had mentioned before, some of these growth factors, so people will also use just like the signals themselves, less than the material. And then finally, this is most similar to some of this coral work, as it's the mineral found in coral, aragonite. This has actually been used for some cartilage repair. So you can already see that a lot of these have been used effectively in the clinic to actually have repair. And some of you may have had even some of these. You never know. There's more and more of these being, more companies making these, and it's a really great, I'd say, progress for regenerative medicine. But back to coral, because that's the main point of my talk, is how can we build a material that's going to repair coral? And so how I started this was talking about the properties of bone and how we want to mimic those. We also want to be thinking about that with coral. So the first thing we want to do is actually see, what is the breakdown of corals? Because corals aren't just these like big structures. They're not plants. They're actually animals. So it's important that we know, what these are made of. And so if we take this coral and we zoom in, you can actually see that they're made up of many almost tiny individual corals called polyps, which they even have this gastric system so they can kind of eat, plankton and whatnot. They have an immune system, and they also have a variety of cells. So you'll see these kind of covering coral. And if you actually look then, again, how does the structure of these look like the structure of bone? So we can see all these individual polyps. We can actually see that the way that our bone is organized also kind of has this similar sort of structure as well. So this is just, this side-by-side comparison of the segmentation that kind of occurs. So it's still all, like these polyps are all still part of one organism, and they make this up, but they work, together, just like our bone is made up of many of these different osteons. And so if we're, again, looking at coral and what of its properties are, and we're thinking back to, okay, people used coral to repair bone, we'd imagine that a lot of these properties must be pretty similar in order to do that. So while coral is made up a bunch of polyps, and these are also made up of many cells, it also has this skeleton behind it. So you can see here, this is kind of a cross section showing, this soft tissue on the outside, and then this skeleton that's on the inside. And then unique to coral, there's some cells that contain algae that are in this symbiotic relationship, and they provide nutrients to the coral via photosynthesis of the algae. So we don't have that in our body, unfortunately, so I can't go out in the sun and, heal myself or, get nutrients, but I wish. But coral can do that. And like I mentioned, they also have a skeleton. And even closer to bone, so they are comprised of also collagen and mineral, so it's just a little bit different. It's aragonite. They also contain bone-specific cells that make mineral. So your body has cells that specifically make bone. You have cells that specifically make muscle, etc. And coral also have that. So they have these very specific cells. And they also use very similar analogs to that bone morphogenic protein 2 that I mentioned before that pushes towards bone repair. And so that's really interesting that coral actually even use some very similar proteins to help them grow. And like I had mentioned, also coral have these immune cells, so they can, respond to, potentially materials as well with their immune system. And so if they've been used for bone repair, what about the alternative? And I put this as quotes again because, I don't want us to think about maybe putting human bones in the ocean, but you never know. But I like to put these side by side again as well. So what we've seen with bone repair is a lot of people in this research base of tissue engineering have taken cells, put these on materials, and then put this back into the person. And with coral, we kind of have this gap right now where we've never really looked into what this material could be to do something very similar for people. So while tissue engineering has advanced the field of bone repair, I really think that it can also advance the field of coral reef repair because we've gotten so many great discoveries about, even something as simple as a metal implant, knowing that, a rougher surface versus something smoother is going to have a very dramatic outcome on your body. And we can apply some of that same learning now towards coral. So kind of getting a jump start rather than trying to discover all these things and how they influence cells, way back like we had to do for bone. Like, let's already take some of what we know that's really great for bone repair and apply it to corals. But before we actually do that in the lab, we need improved methods to study coral and actually engineer these biomaterials. So currently, researchers will take a large piece of coral and they'll propagate this into smaller pieces or fragments. So people will use this to build up coral in the ocean, but they also use this to study coral. Because you can imagine how many corals you might need if each coral you're just using this giant thing, like it's just a lot of waste experimentally. So they break them down into individual little fragments. But you can also imagine you're just waiting for these to grow. And even these small fragments can take months to years. It's really resource intensive, and it's very costly to maintain. So imagine you have all these fragments, and you're either doing it in an aquarium or you're doing it out in the ocean. You have to pay someone to be maintaining this aquarium all the time, and these can be huge gallon tanks, or you're paying somebody to go out into the field and check these all the time. So you can imagine this is just, a lot of money and just a lot of waiting. And so I also believe that tissue engineering can help apply some of what we know and how we study our mammalian tissues to actually even accelerate this process as well. And so this starts by, again, if we're going to compare to what we do for people, so you can actually take the cells of your body, you can put these in petri dishes, and you can study them over time. You can then also put them in three-dimensional materials, which is a bit closer to mimicking what your body is, because as I mentioned, there's minerals, there's mechanical properties, there's porosity. A plastic dish is not going to mimic that, but a three-dimensional material is going to get closer to that. And then there's animals, which are very complex because you have all these cells together, and so specifically, if you're like, I'm really interested in just knowing how one cell is going to respond, that's where cell culture comes in. And so what my lab also wants to do is to try and apply cell culture to coral reefs. So being able to culture these in 2D and in 3D biomaterials so that we don't have to take this huge coral and study that and have to be using tons of these just to understand outcomes of changing climate and whatnot. And so that's where, I see tissue engineering not only as an actual way to repair corals, but a way to also study them. And then for those of you that may not know what cell culture is, as I had mentioned, you can grow your cells outside of your body in an artificial environment that's controlled. It's super common in human health research and has recently even been applied to coral cells as well. So my lab is not the first one to do this. Other people have already started some of this work. And this is a nice image actually showing, this would be a mammalian cell, so not a coral cell, but you can see, we can get really close to these and do a lot of really intense studying. And what this actually looks like in the lab is it looks like they are kind of just these cells, which you can't see by the naked eye, but they're floating in what looks like fruit punch. It is not fruit punch. Do not drink it. It does not taste good, is what I've heard. I, of course, have never drank it. But so this is ultimately what this 2D cell culture actually looks like. And how we then apply this to coral, and so one of my students, Haley, has been doing a lot of this work, so I want to have a shout out to her. But so she'll take these coral, and she can isolate cells similar to how we would do this for people. And then we can grow these over time in, starting with just 2D because that's the easiest, just in these plastic dishes. And so you can see over time, we're getting more of these growing up, which is great. So they're not dying off. And there's a variety of different methods you can use. And again, we can control the conditions of these pretty nicely. So we could change what temperature they're exposed to just by putting it in kind of this it looks almost like a little oven. And then you can also even freeze cells to store them for later, which is really exciting. And that happens a lot in mammalian work is you can take these cells, from someone, freeze them down, and then, years later, bring them back up to study them again. And that's super important, especially if you're trying to understand studies over time. But we've also put these in 3D as well. So this is an example of, what we see with some of these materials. We can do collagen-based materials, and we can put these coral cells on them. And this is just, again, one of those SEM or SEM imaging of how these look interacting with a material. We can likewise then perform fluorescent imaging of these. So the really great thing about corals is that they autofluoresce. And so normally with all the cells in your body, they unfortunately don't fluoresce. So, that's just one of the things you have to do afterwards is kind of make them fluoresce. But coral cells, this is just part of their interaction with algae. And so we can get these really nice images without having to do a lot of manipulations of these cells. But as I mentioned, there was going to be more graphs, so I want to make sure I fulfill that. But one of the really exciting studies we did is we then looked at, again, this collagen plus collagen and mineral, like we did with bone, but then applying this to coral. And instead of using this mineral that's similar to bone, we use the mineral that's similar to coral, so this aragonite. And so we found that over 28 days, our coral cells could grow in these. And you can see here that the glass actually did better than our gels. And so there's obviously a lot of optimization that has to go into this. But we're starting to see some trends with our mineral gel potentially being better than our just collagen gel. But, we didn't settle at that. We wanted to look at some other comparisons between these two gels with coral. And so beyond just coral cell culture, you can also do polyp culture. And so we collaborated with another professor at UCSB, Dr. Adrian Steer. And you can essentially bail out polyps. So all these individual little kind of animals on your coral, you can raise the salinity and they'll just kind of pop off. And so this allows you to get a little bit more maybe realistic study of coral. So instead of just a bunch of dissociated cells onto a material, it's now this more, organism that still has its shape, but you can also look at them on a much smaller scale because these polyps are like a millimeter across. And you can evaluate their health again with fluorescence. So this is an image of what, a bundle of these polyps are kind of looking like after they've been bailed out, and how you can see how nice and green they are and healthy after this process. And so we looked at then putting these polyps on our collagen materials, these mineral collagen materials, and then this calcium sort of control. So this would be what people normally put corals on for propagating these. So we could already see at day 7, at least with these polyps, that we're seeing our mineral is doing really great compared to just our collagen. At day 14, it evened out a little bit, but in general, we're seeing at least a faster rise in their activity with our mineral materials. And if we actually do a side-by-side comparison to what it was at 7 days versus 14 days, we're not seeing really a lot of growth happening in our collagen materials, but with our low and high mineral, we are seeing this significant difference, showing that we are getting some of this better growth and potential better cell activity that's happening on these materials. And finally, we also have looked at putting these fragments on material similar to what has already been done. So just to further compare how our materials relate to what the standard in the field is you can take somewhat smaller, more uniform sizes of your coral, and then you can put them on these materials and then put them in an aquarium. So we actually have an aquarium in our lab. I did not want this to happen because we do a lot of mammalian work as well. And I figured a coral tank mixed in with some mammalian work was maybe not the best thing, but it's actually turned out to be a great idea by my graduate student, as well as collaborations again with other labs on campus. But using these aquariums, we can actually then put the materials in the aquariums to get a little bit more closer to what this would look like in the ocean rather than just in like a dish. And so it's a little hard to see here, but we can monitor the health over time, and we've already seen that there's some dramatic, somewhat remodeling of our mineralized collagen biomaterial, as you can see from the 0 to 2 days, this kind of disappearing as our coral might be using this to help it grow. But again, a lot of these are still really early stage. We've just begun this. So I started my lab about 3 years ago. So we have plenty of time, plenty of space to grow in this field, and a lot of different materials that we want to test. So there's still plenty of research that needs to be done before we can bring this to the field. But I want to also highlight other labs' relevant success in this space because, science doesn't occur in a vacuum. So other researchers have actually used printing to put corals and microalgae into materials. So you can see here they've kind of trapped these algae into the pores of a material. And other labs have also used microfluidics, which is essentially kind of this chip where you could flow fluid through to culture these polyps, so actually give them some sort of forces across them with kind of to simulate the ocean. And then people have also done this for enhancing larvae attachment. So they've actually built materials that could enhance how the propagation from coral can grow, because coral doesn't just propagate by snapping off fragments, so that's like an asexual propagation. It also can propagate sexually through actually making these little larvae, and they found that biomaterials could be made to enhance their settlement, which is super exciting. So I'd like us all to imagine the future of coral restoration. So our current methods are, taking these fragments on materials, kind of waiting for them to grow over time. Whereas I see we could take either polyps or these cells, put them on many more materials, and then hopefully get faster and more corals to grow over time. And so I think of these as kind of next generation repair strategies, because if we can mimic the natural properties of coral, then this should, following a lot of this work that's already been shown in the tissue engineering space, this should lead to a better growth of our corals. And then we can apply all of what we already know about bioengineering and biotechnology to people to then coral reefs. And because they are so similar in structure, as you had seen from some of my talk, hopefully you've seen how close that bone can be to coral and how we might be able to use some of these same materials to repair this. And then again, some of what our lab is developing, as well as other labs, is actual ways to study these on much smaller but more high throughput scales, so that we could really understand in a much quicker way how to repair corals and how they respond to different systems. But as I mentioned, we have a long way to go. I think there's still plenty of space in this field for others to be doing this research, and I hope more and more people do get into the space of trying to use biomaterials to repair coral reefs. So I hope that we can shift this decline into then an increase and a repopulation by working with marine scientists, because I think still so much of what they're doing is incredibly important, and we can't do any of this work without them. And that we could also transfer this, some of these dying reefs into something that then is, brilliant and beautiful again by using these materials. And so beyond a lot of the work that we do with biomaterials for coral reefs, as I mentioned here today from Haley's work, we also do some studies in bone cancer, creating materials for bone repair, and infection prevention and modeling. So still a lot of my work of my lab is human-focused as well, because this is something that I'm still passionate about too, is not just repairing these reefs, but also hopefully repairing everyone that has any kind of damaged tissue. And so I'll end with, what can we all do about this problem and about our reefs? So I think, as many of us might be tourists to these reefs, is practicing responsible tourism. So you can use reef-safe sunscreen, so using some of these minerals instead of some of these toxic chemicals. Being careful where you step or anchor on reefs. So there's been some studies that even show sometimes just a little bit of damage to coral could actually lead to destruction of the whole coral. So even if you think, oh, I've just bumped it a little bit, they can still get infection. They can get overtaken by algae. So we want to just be really careful with any kind of damage that we're putting on them. You can also reduce plastic waste, because this plastic actually influences their helpful microbiome, and so this can cause them, again, to have trouble surviving. And then educating yourself and others, so raising awareness, seeking to learn from experts. I know there's a lot of information out there, and it's trying to find those that are doing a lot of this research themselves. And then supporting environmental policies, so we can advocate for policies to protect these reefs. And then if you happen to have a ton of money, you could donate to scientists to fund their research, as well as training the next generation of scientists, because I hope that it doesn't end here with me. A lot of what my job is besides doing research is educating graduate students and undergraduates, and my goal is that they go on and do even more amazing, even crazier work than what I'm doing. And with that, I would like to thank my lab, our funding, our collaborators, and I'm happy to take any questions. Yeah, that's a great question. So the question was, how do you see applying this in the field if everything is really successful? So of course, I think that's where a lot of marine biologists come in. So a lot of their work is field-based work, and I myself have never gone into the field in that sort of way. So we would definitely want to collaborate with other researchers to actually put these into the ocean, because my goal would be either we can use these in a nursery separately, so to help grow these corals faster, say in aquariums, and then transport them, or actually take the materials themselves with newly propagated corals and put them into the ocean. I think there's a lot of, that will definitely depend on, what we settle on with our solution, because some people are even taking cement structures and they're organizing them in a way that helps for coral. And so we could think about how could our materials even integrate with already existing novel methods as well. But I think it'll really depend on what we decide to do. But I think there are a lot of applications that we can have into the field. And that's my overall goal, is that it gets out there. And that's the big problem is, I've heard that question a lot, is so the question was, if the ocean is, going to continue to be hot and killing these corals, what is basically a biomaterial going to even matter if the coral can't survive that heat? And so I think that's where some of these slow-growing corals come into play, because these slow-growing ones have been shown to be more resistant to some of those changes, and they can actually survive better in those climates, but they grow just so slow that people can't use them as a propagation technique. And we know from some of these biomaterials for bone is that you can accelerate your cell growth, you can accelerate repair by using biomaterials. So ideally, we could use that with a slow-growing coral so that it could grow faster, and then we could use those kind of corals to add into the ocean. But there's other ways, too, that we can do this. Potentially. So there's a lot of actually really, really exciting work that's outside of my realm of expertise in genetic engineering corals. So finding a way that, like, these slow corals have adapted to, be resistant to some of these temperatures. How could we then edit other coral species so that they could do that too and potentially survive in climates that maybe they wouldn't have survived in earlier? So that is something that I would love to, partner with people that do that. I cannot edit cells. I've tried, didn't go so well. So that's somebody else's research, but there's like a ton of people doing that work, and that's why I think like this would be a great synergy with what they do. But great question. Yes, I think I see what you mean. So yes, definitely, like the lab is, like that work is always going to be so important for whether it be probably some of these coral discoveries as well as also human discoveries. So much of my lab also is studying cells in the lab, but like human cells. And a lot of those discoveries can actually help us to create then better materials for human repair. And that's how a lot of these started, is people would culture cells on this like new material. They can culture so many cells on so many different materials, and then they can narrow it down to say one material or two materials. They can put that in animal models so that you're not, having a ton of animals with like all these different materials, and then from there you can bring it to people. And that's how a lot of these successes with these regenerative medicine therapies have actually occurred. So yeah, spot on. I think that research definitely needs to be happening, because I think there will, come a point where, at least in certain regions of the world, we're going to need some of these corals that have been adapted in a way that they can survive. Because there's only so much a biomaterial can do. So some of what I didn't talk about today, but the nice thing also about these is you can kind of put other biomolecules in these. So you could be able to put potentially some molecules that might help them, offset some of these issues with temperature, but it's going to be still really challenging. And so I can't say for sure if we'll need 100% genetically engineered corals, but I think that is definitely a solution that a lot of people are looking into, and I think it's like a worthwhile place to be doing research. So the question is, how long is it going to take me to take all my lab work and then actually put it into the ocean and see some results? That's a fantastic question. And that is the problem with a lot of lab work, is some of it never sees, the light of implementation. But I think since we've already started collaborating with some professors in marine biology that do field work, I actually think that we would be able to test some of these much sooner than I would think, because they go out into the field and they already do some of this work. So, my kind of ideal goal would be 5-10 years from now, probably more like 10 years, but that would be what I would really love to see. And I know that seems like a really long time, but for lab work, that's actually pretty good. At least for mammalian type of work, would be really fast. Yeah, so the question was kind of this algae coral sort of interactions. And so yeah, the algae oftentimes with these raising temperatures or changes in pH will kind of expel the algae, which the coral uses to survive. It still has this gastric system, but it still uses a lot of the algae in this symbiotic relationship in order to survive. And so once it's been expelled, can the coral kind of come back from that? And I think it's a slippery slope, because the reverse can happen, where you can kind of have an overgrowth of algae. And so it's this balance between the two that's actually really important. And so that would be something, one of the things that we would be looking at too is like, would our materials promote this balance, or are they going to shift it one way or another? Because you could think if they shift it one way, it could potentially still be good if it's in that kind of situation where it's shifted already the opposite direction. You might want a material that, say, brings in more algae. Yes, I guess is your question, like, if you have a bleached reef that doesn't have any coral on it, can that still be used as, like, can you still get cells in there? And that's something, we've thought about as well as, like, why doesn't that happen more? Like, why is it, with these bleached reefs, we're not just seeing, more of this coral just settling back onto it or whatnot? And I think, like, it could be due to there still being some missing signals there that can help them to grow, because it seems still like coral needs to be producing some of the skeleton, like that's part of its like growth, and just using like another skeleton, I think it needs still something more for its growth. There's still the potential that we could apply some of this to your already bleached reefs and whatnot. But most of what I see this as being useful for is taking like those already like, a healthy fragment and doing a repopulation. And, there'll still remain some of these skeletons and whatnot. And I think the other potential part that you could apply these to is if, say, one of these were damaged, whether, it's from hurricane or it is from, somebody dropping an anchor on that sometimes this leads to the death of your whole organism. And so using a material to help then get it to repair rather than to continue dying off. Yeah, great question. So the question was, can you apply this to all of the, tons of corals that exist in the world? Like, is this kind of like a universal application? And I definitely see this as, it's probably going to have to be tailored to some different species of coral, because just like, all people are different. And if I make a material for bone repair and I put it into myself and my friend, we both could have very, very different responses because we are just different. And so I could imagine some of this potentially being a little more personalized to the coral species. There's also coral that don't make a skeleton, so there's still like soft corals. And then, like you had mentioned, there's slow and there's fast, and the way that those grow, they might need very different nutrients. So I think that would definitely be something that we'll have to look at optimizing. But, for now, starting small, having like one or two species of coral, seeing if that can work, and then, going from there.